Hello Math 263 students. In this video, we'll take a look at 2.1 and 2.2. This is a screencast, meaning as I move the cursor, you guys can see what I'm pointing to here on the screen and also hear the audio. So hopefully this will work well to go over some of the problems that we would have done in class today. So let's get started. Chapter 2 is all about nonlinear functions. We'll cover quadratic, exponential, logarithmic, and also rational functions, and a few other types such as step functions and other miscellaneous types thrown in. So in the real world, most of our functions are not perfectly linear. We might have sections, like this section right here, where we could approximate the function with a linear function, but over the whole course of the growth, one single linear function would not fit very well. So we want to try to figure out what sort of models are going to work for us. And then thinking about business, we'll talk about profit, cost, and revenue again. And we'll also talk about such things as interest, which will tie into our exponential functions at the end of the chapter. So 2.1 goes over properties of functions, and then 2.2 will focus on quadratics specifically. We want to remember that a function is just a rule that assigns to each element from one set exactly one element from another. So think about the one set we typically call our domain, and then the other set is our range. So we'll have a rule that assigns each element in our domain to exactly one in our range. Great. So this slide just kind of recaps that we can also talk about independent variable as domain and dependent variable as range. So when we look at our function, usually, or a graph of our function, our independent variable is on our x-axis, our dependent is on our y, and then we'll look at a lot of time series data, just like we did in chapter 1. Sometimes profit, cost, and revenue. We'll talk about number of items on our x-axis. And to illustrate what's going on with our domain and range, think about we can get an x value or a t value, a time value. And if we know a time, like 14, we can read off the y value. And if we know a y value, we can read off a t value or an x value. So we want to feel comfortable being given domain values and finding the corresponding value in the range, or given a value in the range and finding a corresponding value in the domain. We want to make sure we can do the same thing on our table. Here we have our list of discrete points and then values here. One thing I want to point out about this table is notice for each x value or t value, there's exactly one y. That's the definition of a function. But we're allowed to have two y's that are the same that correspond to different x values. We'll talk about that concept a little bit more as we go along as well. We could also be given our function with a mapping diagram. And in this case, I said function, but we want to ask ourselves, is it really a function? So notice 16 goes to 60, 7 goes to 12, 9 goes to 12. This idea of 7 going to 12 and 9 going to 12 is kind of similar to the idea of the 0 and the 1, both mapping to the 13,104.14 in the previous. And then notice we have 43 maps to 19, 28 maps to 19, but notice 28 also maps to 27. So here we have an illustration of one item in our domain that maps to two items in the range. This is a problem. Here, this is what is not allowed for a function. If we had removed one of these, like the 28 mapping to 27, we would have a function, right? Two things in the domain mapping to one in the range is fine, but one value in our domain mapping to two different in our range is not okay. So we want to be a little bit careful here. It says functions, but this is indeed not a function. So looking at our graph, we'll talk about vertical line tests in a little bit, but we can look at our graph and say, okay, each x value, if I trace along, there's only one y value. I'm not getting two different places on my graph that I'm looking at. Whereas in this one, notice we're thinking about if I have an x value of 4, they put those points on there, it maps to 2. But if I also have an x value of 4, I'm getting a mapping to -2. And in fact, this happens at every single point except x equals 0 on our graph. So this one is not a function, whereas our previous parabola that opened down was. So horizontal and vertical lines can be a little tricky. For our horizontal line here, think about your individual x values. For an x value of 2, that maps to 7. 4 maps to 7. 6 maps to 7. Each x value maps to one y value, exactly 7, and they all map to the same. The fact that they all map to the same is okay. It's the same concept as when we were looking at 7 and 9 mapping to 12. It's just every single domain value maps to 1 in our horizontal line. So a function like this, and here I said function, but we do want to be a little careful. With this one, notice if I trace along any x value, it's only mapping to one y. Again, we can think about that vertical line test. If I think about one x value, that's the concept of putting a vertical line, and it only intersects one time at each place. So let's take a look at this box. Unless otherwise stated, assume that the domain of all functions defined by an equation is the greatest subset of real numbers that are meaningful replacements for the independent variable. So what does that mean? It means a couple of things. We care about what the domain is, and we'll look at some different examples of that. But it also says meaningful replacements. We can interpret this a couple of ways. We'll have some algebra functions where substituting particular values causes the function to be undefined. That's a problem. But we'll also have real-world context problems where a negative x value or particular x values aren't meaningful replacements. So we have to be aware of two things, sort of the algebraic restrictions on a function and then the context restrictions on a function. So I'm going to take us back to some of our previous examples just to talk about our domain and range. So again, for this mapping, it wasn't a function, so we're not really going to use the concept of domain here. We could still talk about the range. We could call this a relation instead of a function, and then talk about domain and range of the relation. But we don't really do that a whole lot in this course. So let's take a look at another example. For our domain for this discrete example, we would have 0 through 7. But our range, we would list out the values that don't repeat. So we don't have to list the repeated values, only one of this 13,104.14. And down here we have 3 days that map to the same value. We would only need to list once. In a graph like this, it's a little bit trickier. Your domain values, since we're continuous, looks like we have 0 through 365, whole year. But then for our range values, notice we have a break in our graph, and it looks like to me it maybe starts about 13,100. And then we're hitting all of those y values in between up until about maybe 16,500. So we could write our range as an interval using interval notation and go from 13,100 to 16,500. We'll get into a little bit more of interval notation as we go along, but we do want to feel comfortable with writing the domain and range as intervals instead of discrete points. Let's look at one more. Actually, let's look at a few more. For this one, notice our x values can be anything. You could be the values described by our tick marks, but you could also be 1, 1.5, 0.7. So think about our domain in this case as all real numbers. My line is continuing in both directions. There's no restriction on my x, and there's no context restriction. And then my range would just be a single value, the discrete point of 7. Taking a look at this one's different than some of our other graphs because we have endpoints. So my range, if you think about tracing down to the x-axis, my x values go from -1 all the way to 4. And then for the range, think about tracing your y values. And I like to do this bottom to top. So if you just think about endpoint to endpoint, this is not your lowest y value. Your lowest y value, think about projecting onto the y-axis, is 0. And we're really going from 0 to 3. So 0 to 3 would be my range. So let's go ahead and pick up with the example after our statement here. In this case, we have a domain that would have our x values, -2, -1, 0, 1, and 2. Notice each of those get listed and none of them are repeated. And then for our y values, think about just projecting these points onto the y-axis. So I have 0, but then both of these points get projected onto 1. Both of these points get projected onto 4. So my range is 0, 1, and 4. Some of our trickier examples will be when we get into rational functions, dividing functions, or functions that are not rational, but sort of a variation of rational, something divided by a square root on the bottom. And this one we can often help analyze with Desmos. You might have an idea of what this looks like just looking at the function, but rational functions can be hard to predict and difficult to look at. We'll learn a couple tips. One thing to be aware of with any sort of division function, whether it's rational or in this case a variation on a rational function, is places where the denominator is 0. So if you were to substitute 2, for example, we would get 2 squared minus 4 is 0. The square root of 0 is 0, and we have a problem. The other thing to worry about when you have square roots is having negatives under your radical. So anytime this x squared minus 4 dips negative, we're going to have a problem. So we'll want to try to combine those two ideas to write the domain. Let's take a second and go to Desmos, just look at the graph of this, and then we'll analyze what they're saying. Notice they have those -2 and 2 values in there. But again, the graph is going to help us a little bit more. All right, so I graphed my function. Notice you want to be a little careful with Desmos that everything you want remains under that radical, and then your function looks like you want it to. So notice what happens is I have this behavior that shoots up, and then I kind of have a desert in the middle. Nothing happening right here. So notice the function is defined from -infinity, keeps on going if we were to scroll out, all the way up to -2, but it looks like there's a problem at -2. If I were to substitute -2 in and square, that gives me 4. 4 minus 4 is 0. And then the square root of 0 is 0. So I've got an undefined function at 0. So we would say something like the function is defined from -infinity to -2, non-inclusive. And then the same behavior is happening at 2. We have a problem as we get close, but as soon as I put something slightly bigger than 2 in here, then I can evaluate my function and I don't have a problem. So what's going on in the middle here? Let's substitute a value like x equals 0. If we put in x equals 0, I would get -4 under my radical, and then I'm doing the square root of -4, which is a complex number, we could say imaginary number in this case, and my function is not defined. If I put in 1, 1 squared gives me 1, minus 4 gives me -3, and I've got a negative under the radical. So this entire region from -2 to 2, non-inclusive, I have imaginary values when I evaluate, so those values are not, or -2 to 2, those x values are not part of our domain. So again, we'll take a look more at things like this later in our chapter, but graphing this on Desmos can confirm what your algebra is telling you. So notice the slide goes ahead and says our domain is -infinity to -2, non-inclusive. The union symbol, so it means and, to infinity. Right, so this is a good place to pause part 1 of our video. There's a 15-minute timeline, or 15-minute time limit. So I'm going to pause this, and then we'll take a look at the rest of our 2.1 and 2.2 in the next video.